additional instruments beyond the overview that we got earlier, because there's been excellent science returned on all of them, of course. So our next talk is on a mission that hasn't launched quite yet, but it is just about to launch not too many weeks from now, the LADEE mission, and the talk is going to be given by Rick Elphic, who is the project scientist for LADEE here at NASA Ames Research Center. So Rick, go ahead.
Hi, good morning. Yeah, so LADEE's next on the agenda to go into space in the planetary arena. And this will be familiar to many of you. And if, let's see, I'm trying to advance here. There we go. So most of you know that the two chief scientific objectives of the LADEE mission are to, one, characterize the lunar atmosphere, and the second, to go after this putative lofted lunar dust that has been speculated on over the years. But it's doing more than that. Obviously, we're killing a number of birds with this particular mission, including testing the first deep space laser communication capability with really high bandwidth, hundreds of megabits per second potentially, which could really pave the way for getting a lot more data down from deep space. LADEE is also meant to demonstrate that we can do a low-cost lunar orbital mission for around the price tag of about $250 million. This says launches in mid-2013, so as long as you consider early September, mid-2013, then that's still true. One thing that's not on this particular list is it's the first launch of a Minotaur 5. This is a Peacekeeper 3-stage missile with two solid rockets on top, and I'll talk about that a little bit later in the talk. So, as most of you know, surface boundary exospheres are found throughout the solar system. There are hundreds of outer planets, moons that fall into this category, and of course thousands upon thousands of large asteroids, or asteroids of any size, that will have, to one extent or another, surface boundary exospheres. These are collisionless atmospheres. They're so tenuous that the molecules don't collide with each other. Rather, they are either lost directly to space or collide with the surface. And their transport in between those collisions is ballistic hops around the surface. The moon is the closest example of that. And as Dave Page was saying in the last talk, it's nice to have one so close by that we can get to quickly and monitor very easily and learn something about the physics of surface boundary exospheres elsewhere in the solar system, Mercury, Europa, and so forth. Then there's this question of dust, whether dust is in motion. Is this something that's a hazard on the surface of the moon? There was a recent conversation going on the Lunar List server about the dust on the Surveyor 3 that the Apollo 12 astronauts visited way back in '69. And that's still an open question. The Apollo astronauts saw some kind of horizon glow from high altitude, and so LADEE is meant to go and address the question and discover, one way or another, whether there is lofted dust or not. Most of you know that there's several constituents to the lunar atmosphere during Apollo. Argon-40 was recognized as well as helium. And then later, telescopic observations, Earth-based telescopic observations, including sodium line imagery shown here, revealed the extensive sodium atmosphere of the moon and potassium as well. So these form some of the key atmospheric constituents that LADEE wants to go after and characterize more thoroughly and synoptically from orbit. Then there's this question of lunar volatiles. We know that there's hydrogen at the poles, and some of it's in the form of ice. LCROSS revealed that to us. But it's elsewhere. It's all over the moon. You can see the signatures in the near-infrared of hydroxyl and H2O absorption. And there's a lot of questions, of course, about what this actually represents in terms of abundance. But if the point is, if it's mobile, if any fraction of it is mobile, then it can possibly make its way and get cold trapped up at in the lower temperature regions that Dave Page was talking about just a little while ago in the North and South Poles. And so the question that LADEE would go after is, do you see H2O or OH in the lunar atmosphere in measurable abundances, and what does that mean for this kind of transport and ultimately for the population of the cold traps at the poles. Okay, getting back to dust. I kind of regard dust at the moon as kind of in two categories in terms of a phenomenon. There's Surveyor 7 and other Surveyor post-sunset horizon glow monitoring. This shows you a series of 4 images from Surveyor 7, the last of the surveyors to land on the moon, showing a little over an hour's worth of imagery of the horizon glow and showing you basically how it changes fairly remarkably as time goes by, much as you would expect for the slowly setting sun to illuminate a suspended dust curtain just a few meters above the surface off in the distance. So that's one kind of dust levitation that seems to be going on, at least you can explain it that way. Then there's this question of the high altitude dust, and yes, this image right here, which is a star tracker image from Clementine, does not necessarily show a high altitude dust. You do see the zodiacal light. This is something that LADEE will see as well. That there might be a faint horizon glow or not. That really is still a question. And current observations from LRO, for instance, are casting some doubt on whether there's a measurable amount of suspended dust at these high altitudes. But this is something that LADEE will address very directly with its measurements. There are predictions for what those densities ought to be on the basis of the Apollo 15 orbital photography observations. And these densities are quite low. These are just a matter of a few particles per cubic meter, a few hundreds of particles per cubic meter. And the higher you go, the smaller the density, and so the harder to measure these things. Down closer to the surface, the densities ought to be higher and should be measurable by remote sensing, but of course that's below the LADEE altitudes until we get to the very end of the mission during what is cutely called decommissioning, where we're getting ready to impact the surface. We can fly through this region of space and actually make measurements there as well with the payload that I will tell you about in just a minute. So here's the spacecraft as an overview. It's just, again, a CAD drawing of the thing. The ultraviolet and visible spectrometer is one of the instruments for remote sensing of dust and the lunar exosphere. Here's an in situ dust detector, the Lunar Dust Experiment from LASP. We have a neutral mass spectrometer from Goddard on there. The UVS is from Ames. The LLCD is the LaserCom demonstration system, and that's mounted on the opposite side from the neutral mass spectrometer. And you can see the rest of the systems. Our large orbit control system is the main system that we use in order to get into lunar orbit, and the RCS thrusters are used for smaller maneuvers. Star trackers, the usual things, antennas and stuff like that. So this is what LADEE looks like. It doesn't have any. It doesn't have a large solar array that's gimbaled, such as LRO does. It's got arrays all over the surface of the spacecraft, so no matter what its attitude, it is power positive. Here are the 4 instruments aboard the spacecraft. The 3 science instruments are the neutral mass spectrometer I mentioned earlier, the UV, the visible spectrometer, and the dust experiment with their PIs here. There's in the lunar LaserCom system. Comes from MIT, Lincoln Labs. I didn't mention that earlier. So that's the family of instruments that are flying on the spacecraft. How do we get up into space? How do we go to the moon? We're using the first launch of the Minotaur 5. Orbital Sciences Corporation has a contract with the Air Force to refurbish Peacekeeper missiles from the old inventory of ICBMs, which is a 3-stage system, and it goes very, very quickly. And then on top of that, there are adapters for, in our case, a Star 48 solid rocket motor, then through an adapter fitting, pardon me, up to a Star 37 solid rocket, and then on top of that sits the LADEE structure. So this is the 5th stage, and this is what boosts us into a high altitude orbit. This is LADEE down at the Wallops Flight Facility. We're launching out of Wallops. This is the first planetary or deep space launch out of Wallops Flight Facility in Virginia, which makes it within driving distance of Washington, D.C., so we expect a very large number of folks to want to go and visit the launch when it happens. The launch will take place at the window opens at night, and so it might be a very, very spectacular night launch for the first Minotaur 5 launch. Here's LADEE spinning on a spin table. This is one of several spin tests. This is just the LADEE mounted to its adapter ring here. The 5th stage would go under that, and there will be a further spin of that, and then of course, once fueled, there will be additional spin balance tests. Here's kind of our mission profile. We go into orbit, basically launched off of the Minotaur 5 into phasing loops, and this doesn't do justice to the altitude of the phasing loops. We actually go out quite far, in the third case, almost to the distance of the moon. But we do these phasing loops in order to check out the spacecraft and make sure everything is working properly, get everything checked out and ready to go. And then on the third loop, we actually do a perigee maneuver here that takes us out to an orbit that will intersect the moon at the right place at the right time. Once we do that, we go into lunar orbit with a highly elliptical orbit initially, and then eventually lower our periapsis and apoapsis down to lower altitudes. And then after about 100 days of science activities, initially there will be about 30 days, 40 days, perhaps as many as 50 days of commissioning activities, during which the laser comm system is activated and checked out and run. And then that's followed by 100 days of the science observations, 3.5 lunations, followed by a few days of orbit decay, and then that's followed by impact into the lunar surface at some safe-to-impact site far from the Apollo and Luna and so forth, legacy sites. So, what is LADEE going to see? I'm trying to paraphrase what I've heard folks report from LRO LAMP and others. They definitely see helium. We expect to see helium there, and it varies with the plasma environment, which indicates that there is a big part of the helium comes from the solar wind, which contains alpha particles from the sun, and so it's not a surprise that that should be a contributor to it. But another big question is any helium leaking out of the interior of the moon? There are radiogenic elements in the moon. We expect to see helium as well as argon-40. The limits on argon-40 are being pushed down. I think that was mentioned earlier by Jasper. And so the question is this a big change since Apollo, and what do we expect to see? Well, on LADEE, we'll definitely be in a position to monitor the argon over 3.5 lunations and see just how it varies and whether it really is different from the Apollo time period or not. Right now, I'm interpreting what I'm hearing from the various folks on LRO to say that there's very little evidence to support lofted dust at the McCoy et al. Densities. That is the model for the scattered light that was seen from the command module and by photography. So the jury's out. I mean, we're in a really good position with the instruments that we have on LADEE to check this story out and even make in situ measurements at very low altitudes. But we'll just have to wait and see what we see when we get there. And we're now in final preparation for launch. We're going out of Wallops. The window for the first launch window opens on September 6th local time. It's September 7th UTC. So it'll be at night, 11:30 or so local time when the window opens and launch takes place. Now, I want to move on and just, since most of you have heard a lot of this before, I just want to show some animations that are kind of in work. This is LADEE in cruise on its way to the moon after the last phasing maneuver. And it doesn't actually spin this quickly, but it will spin at about 1 degree per minute or so. This is for thermal balancing of the spacecraft. The spacecraft was basically designed in order to operate in low lunar orbit around the moon, primarily in the RAM attitude. So the thermal design is really for that. And in order to manage the thermal situation in deep space, then we slowly barbecue mode roll the spacecraft about its z-axis. Okay. And this is LADEE's not actually in the proper attitude to go into orbit around the moon, but this is like what LOI would look like. Lunar orbit insertion takes place within view of the Earth, but after a period of being out of view of the Earth. We'll have about 5 minutes of visibility from DSN before we light up the engines. Then we go into this eccentric orbit, and that's followed by a series of ever lower orbits around the moon that bring us eventually into our 250-kilometer commissioning orbit. And then after that, we drop down into very low altitude. This depicts the operation of LDEX, the dust experiment. As we are orbiting now low over the lunar surface, the dust particles come in and create, they impact the back end of the witness plate back here and create little plasma clouds. And the ions in the plasma clouds are drawn to this negatively charged anode up at the front of the thing. And that's how we count dust particle impacts and get actual dust densities while in orbit around the moon. And of course, that'll still be operating as we descend down to the very lowest altitudes prior to impact on the lunar surface. And with that, I'm done. Any questions?
Thanks, Rick. Excellent. Well, your talk has generated quite a few questions online, as a matter of fact. And let's see. I'd like to start with Clive's question, if we can scroll up. He's the first one. Okay, hang on just a second. Here we go. So questions for Rick. One, what surface mission would you envisage as a follow-up to LADEE that would maximize the significance of the LADEE data? And then two, in your experience, could Minotaurs be used to put small payloads on the lunar surface? If so, what would be the maximum size?
Wow, a bunch of good questions. I'm torn for question one as to what the next mission ought to be, because I'm very, very interested in going to the poles to find out what's going on there. On the other hand, there are lots and lots of lower latitude lunar surface missions that would benefit hugely. If we don't see dust at high altitudes with LADEE, that doesn't mean that lofted dust doesn't occur and that whole electrostatic process doesn't occur. It could be the surveyor situation that obtains. And so I would say that, to cut to the chase, having an imaging system and a dust detector on a landed system at low latitudes in order to check out the surveyor measurements, we haven't had something similar on the lunar surface for decades and decades. That would tell us a lot about what's going on. Probably answer that question, and it would get to the question of whether lofted dust actually does present a hazard, whether Surveyor 3 was actually covered with dust and dusted off by the descent module, or what was actually going on there. There's a lot of controversy about that. Yes, Minotaurs could be used to put small payloads on the lunar surface, I believe, if they're small enough. What would it take? I don't have those numbers, Clive. We can look into it. As you know, there was a design for LADEE with legs back a few years ago, and that kind of turned into the Mighty Eagle down at Marshall. So we might ask that question of them as well, but I'll try and get an answer for you. I don't know how big it would be. That would be a system that would actually be able to get you a soft landing on the surface.
Okay, great. Thanks. Let's take a couple more questions. There's one from Ahmed Sharif, which says, in the previous image to the right of LADEE, why was it spinning? I think you might have answered that with the testing, but then is that a standard test you run on all satellites? If so, then what for?
In this case, LADEE's fifth stage is actually spun up prior to firing the engine. The Star 37 is a spin stabilized stage, and so we've got to be spun up to fairly high revolutions. And so, because that's part of the launch profile, we have to test it prior to launch, both unfueled and fueled. And so we take it in steps. That's what the explanation is for that. Obviously, if your launch profile does not include a spinning stage, for instance, the Centaur used on LRO was not spinning. It's a 3-axis stabilized system, and so no de-spinning, no spin tests would be needed for that. I don't think. I might be wrong about that.
Okay, and then I'm going to take one more, and then the rest, maybe what we could do is, if you wouldn't mind answering them in general chat, that would be great. So the last one for this is from Carly Peters, and she asks, Rick, can you say more about the LaserCom? Will it be brought to flight readiness, and when might it be used for future missions?
Well, the answer to that is that the LaserCom system that's on LADEE right now, while it's a tech demo, is flight qualified. I mean, if by that, though, you mean actually used for mission telecom purposes, data communications and uploading commands and stuff like that, that's not planned for LADEE. It will send test data down, and it can send independent pieces of what's in memory on the processor side of the spacecraft to get a fully independent, basically, image of those partitions.
Hello, welcome to the conferencing system. To join a conference, you may use the far-end camera controls on your remote. Please enter the conference code now.
Time for your team, I'm sure, and so if you wouldn't mind answering the rest of the questions in general chat, that would be great. I want to encourage everyone online to continue chatting on general chat. This is why we created these two chat windows. So please have at it. So anyway, that ends all of our mission talks, but we do have one